All right, welcome to the first part of the Introduction to Algorithms. We are moving out of the section of the course where we were beginning bioinformatics. So we've learned a little bit of Unix, we've learned a little bit of Python, and now we're going to put that into practice by learning some algorithms and how to use that programming knowledge that we have to do some useful stuff in bioinformatics. The tasks, the Rosalind homeworks, are going to get a little bit more difficult. They're going to assume that you have some mastery over the stuff that we've done before. Throughout the notes, I'll have pointers to some of that stuff back in bioinformatics, the beginning bioinformatics tutorials. But if you find yourself getting stuck consistently, you may want to go back and redo or go over some of those introductory tutorials again, just to make life a little bit easier. So first thing you'll need to do is go to the module in Canvas and get the Intro to Algorithms Part 1 PowerPoint. So from now on, things won't be so much in Word. I've got them in PowerPoint as sort of more traditional lecture style slides, although they're still kind of in the walkthrough format. So let me start sharing the screen here. So once you get that PowerPoint for part 1, you should get to this slide. And a lot of the ideas for this, obviously, they go along with the Rosalind homework, and the Rosalind homework, at least the sections that I've pulled out, also go along with this textbook. I think now they've put this in, that maybe the 3rd edition is the single volume. It used to be 2 volumes, but in any case, we're kind of starting at the beginning with what they call the algorithm warm-up. It's kind of a cool section. If you go to the website, you can basically access the whole text. So they've got lesson 1.1, and there's lots of interesting information here. I find that their approach, because the people behind the textbook and behind Rosalind are computer scientists who work on biological problems, a lot of their presentation is geared toward computer scientists who are bridging into biology. And I will really emphasize sort of the other direction, a biologist coming into computer science and making those connections even more simple. A big part of what's in the textbook and, the first part of these PowerPoint slides is bioinformaticians, one of their values is learning how to translate biological problems into computational problems, or vice versa, right? Otherwise, you just need a biologist or a computer scientist. That's the real value of somebody who I feel like is a real bioinformatician, is somebody who is really adept at identifying a biological problem that we can answer computationally. So how do you turn a biology question into something we can compute, or something we can solve with computational methods? There are lecture videos that go along with all of the chapters. I am not going to get into as much depth as they do, because, well, partly because their lectures are here. So, right, there's a whole YouTube section that goes along with chapter 1 here, and I encourage you to watch that because they'll go into more depth in the, again, sort of from a computational biologist perspective, how do you translate, like, what does the biology mean, and how they're translating that into a computational question. So, all right, you can watch it right on their website, or you can go to YouTube and watch that. This is Pavel Pevsner. He's one of the authors there. He's the sort of PI, really well-known, well-respected bioinformatician, has trained lots of postdocs and PhDs, and really sort of influential figure in at least in the training of bioinformatics. So first chapter is all about how do we find the origin of replication in bacteria especially. It focuses on prokaryotes because, you know, the genomes are a little simpler. Eukaryotes have multiple origins. We're going to avoid some of that messiness, at least to start out with, because really, although we're applying sort of computational methods to biological problems, we're going to try to simplify the biological problem at first. And that's often what you have to do in order to apply these computational approaches, at least at first. Okay, so the idea here, right, is this bacterial genome needs to replicate itself, and where does it start? That is the question. So, right, where is the origin of replication in the genome? Origin of replication is going to be abbreviated as ORC. Now, as a biologist, you might think about wet lab ways that you could approach this question, right? You could do some kind of mutant screen and look for colonies that can't replicate as well. And, you know, not that it makes it easy, but at least you have some wet lab methodology in mind where you could approach trying to find where in the genomes are affected, where do the mutations happen that are associated with mutations that inhibit replication. Okay. For a bioinformatician, right, this is not a computational problem, right? Where in the genome is the origin of replication? Well, there's too much that is undefined here in computational terms. So, right, we've got Captain Picard, right? The bioinformatician is just saying, you know, what's with all the acronyms? If you've ever been in a developmental biology talk or something like that, where they throw out a lot of gene names, that's how bioinformaticians feel all the time when they talk to biologists. So, first step, right, we can ask in defining this computational question, well, how does the cell know where to start replication? And we can at least get down to a window of DNA sequence to say it probably starts somewhere in this region. Okay. And so there's something in this region. Okay, so we'll talk later about how we can define this region, but for now, we'll just assume that we know that the origin is somewhere in this section of genome. There's nothing about 500 nucleotides that's magic. It just happens in this example of the cholera bacteria, Vibrio cholerae, that we know it's in this origin of replication window. So there must be some hidden message in there somewhere. Okay. That's better. At least we know that there is some string, right? So this is we can read this as text, right? We can define this computationally as a string of DNA. We've dealt with this already in Python a little bit. We could even manipulate this with BioPython in some ways. Okay, but we still have this sort of nebulous idea of what is a hidden message, right? If the cell is recognizing something in this sequence, how do we approach figuring out what it is in this sequence that the cell is recognizing? So hidden message is not defined, so the bioinformatician is still saying they don't really understand. And then this example is from the textbook. They talk about trying to decipher hidden messages, right? So what is it about a message that really, you know, at first seems like it has no pattern, but we know there's a message in there. How can we work to decipher this? Okay, and it's actually the gold bug story message. And there's a long, and again, go watch the video from them to find out more of the background here. But the hint is that the message is in English, and you can start to recognize that some sequences are occurring frequently in this message, right? So why is semicolon 48 so common in this sequence? Okay, and obviously you wouldn't recognize this right away, but if you stare at this and try to decipher this message long enough, you do start to see patterns, right? And colon 48 is a recurring pattern in this message. Okay, and in particular, right, 4 and 8 occur really frequently. So if we also know, because this is English, that the word the is the most frequent word in English, we can test whether THE is, well, we don't test it, but let's say that colon 48 matches with TH and E. Then we can go back through, and based on the fact that this is the most frequent pattern in the code and THE is the most frequent word in English, rely on that to say, okay, this is the key, right? This is the hidden message in some sense. Now we can break the rest of the message. So we could then go on to assign all the 8s are E's, all the 4s are H's, and so on. And you can go in and watch the rest of the video to say you can extrapolate from that to really break the rest of the code. So the reason this is important is we broke this code just based on defining the hidden message as something that occurs more frequently than you might expect. Right? So finding common patterns in the string. Okay. So if we take that intuition or that methodology for code breaking into how does the cell know where to start replication, we can now again start to approach this question, right? We've got the string, that 500 base pair region, and a hidden message in there that is text, okay? And so if we apply that, the Goldbug method, right, the frequency sort of approach, we can ask, do some words, or we'll start using the word k-mers. That's just a K is any number of letters in the DNA. So a word of any length, does it appear surprisingly frequently in a small region of the genome? So in this case, the 500 base pair sequence. Okay. So in this pretend sequence at the bottom here, AATTT is surprisingly frequent 5-mer, right? So the k-mer here is 5. And so if this were a sequence in, if we extend that to finding the origin of replication, right, we might say that our hidden message is AATTT. So maybe there's something that Vibrio recognizes as AATTT that's causing it to recognize that sequence. Okay. So how does a cell know to start replication? There are hidden messages. What is a hidden message? Well, we're going to define it as the most frequent k-mer in a given sequence. Okay. So for a given origin of replication, that 500 base pairs, if we find the most commonly repeated pattern of length k, we find how does the cell identify that start of replication. Okay. And then again, it's that same example. If we define that, right, we've shrunk it down from 500 to whatever this length is. and we find that this thing is overrepresented, that is the hidden message. That is how it recognizes this as the origin of replication. Well, does that make any sense to the bioinformatician now, right? And indeed, this is a pretty well-defined computational problem now. We've got a string, and we just want to find what's the most frequent k-mer in that string. So, the string we're calling text, okay? And so let's find what's the most frequent k-mer in there. And that also makes sense biologically if we think about how transcription factors work, right? If replication is performed by a DNA polymerase, okay, we know that replication is mediated by this DNA protein, okay. This transcription factor typically binds sites that are 9 nucleotides long, so we might expect our hidden message to be 9 nucleotides, but we don't even need to assume that right off the bat. We can just design an algorithm that recognizes frequent k-mers of any length. In this case, you know, DNA A, you might expect the k-mer length k to be 9, but we won't specify 9 to begin with. We'll let it find it at any length. Whoops. Okay, and again, biologically, what does that mean? When we find a frequent k-mer, it's finding the transcription factor binding site. Okay, and just to make this potentially more interesting to any of you who are doing this kind of work, right? This method can be extended to potentially find transcription factor binding sites for anything. It doesn't have to be origin of replication. For example, if you had RNA-seq data so that you could identify clusters of co-expressed genes that always go up together or always go down together, etc., you might expect that those clusters of co-expressed genes have a common transcription factor. And so you could take, say, the upstream 1,000 base pairs of all of those genes that are going up together and say, are there any frequent words that these things have in common, and identify a regulatory site even when you don't know what the transcription factor is. Okay, so this is hopefully starting to make some sense of how we've taken a biological question, what's the origin of replication, and turned that into a computational problem. What are the most frequent k-mers in a string of DNA or string of text? Okay, and then that, you know, can then be flipped to an even more general biological question about finding regulatory elements in genome sequence. All right, so that's the general background. Again, go watch the video for chapter 1 of the textbook, and you'll get even more background and some insights on the mechanics of that. But Rosalind number 10, let's start working on the problems. Okay, so Rosalind number 10, let's take a look here. I'll let you read the background at the top. It gives us some pseudocode here, but then this is the real problem. Okay, so we're going to be given a DNA string, but actually 2 DNA strings. One is the text, that is a sort of, you can think of that like the genome sequence, and then the pattern. And we need to return the count, or how many times does that pattern happen in the text. Okay, so just like up here in our notes, right, how many times does this pattern occur in this text? And our count would be 1, 2, 3. Right, so that's what we're trying to get to. The cool thing about starting here is that this introduces a really common algorithm. It's useful for all kinds of analysis when we're talking about DNA, RNA, protein sequence analysis, and that is the sliding window algorithm. And that's pretty much what this pseudocode is showing you with the sort of simplest analysis that you could do, and that is just count how many times the window matches some pattern. So how do we code a sliding window? Well, I've taken apart their pseudocode here. Let me open a Python window, spider window. I might have to shrink this down. It won't be too small. Okay. So the first thing we're going to do is initiate a count, right? Because that's, we're just going to say the count is 0. Now, the name sliding window comes because we need to slide across the text, right? And in this case, our sample data is, let me blow this up a little bit. Right, the sample data is GCGCG. Okay. We need to slide across that text and count how many times does this pattern match. So for our example, just to make things easy to start with, I'm going to hard code the text and the pattern for the sample data. And I think I got that right. GCGCG is text and pattern is GCG. Okay. I'll make it pretty. All right, those spaces don't matter around the equal sign, but just be consistent. Being consistent. Okay, so how are we going to slide across the text, right? The first thing is we need to slide. Now, we could, you know, going back to Python section 20, I don't remember if that was part 5, maybe. How do you slide across text? Well, a pretty, whoops. Or I talked about one of the things Python's great about is we could just write a for loop, 4-letter in text, and then do print letter. And Python is so smart, right? We hit play. Whoops, forgot my parentheses. Told you I would do that a lot of times over the semester. Right, and hopefully you can see that. Right, Python is smart. It knows how to loop across a string. GCGCG is my output. Okay. Unfortunately, that super simple, straightforward way doesn't really help in this case because we need to get windows that are the same length as our pattern. Okay. So there might be a way to hack that that I don't know of to make it grab 3 at a time. But I don't know a straightforward way, except the way that I'm going to show you to get the windows. Okay, so we need to, that simple way of just the sort of internal method for Python looping over a string isn't going to get us a sliding window. Okay, because it doesn't get windows, it only gets one character at a time. So what we need to do, right, is our first window, we need GCG. And then we need to move over one base pair and get the next 3. And then finally move over another base pair and get the last 3. So the question is, how do we specify the loop so that it gets each one of those windows? Okay, so first thing is recognize, how would you make it print just this window, for example, right? We could do, okay, come over here and do, let's get rid of that. That's not going to work, is it? Oh yeah. Oh yeah. Right. 0, 1, and 2. I was thinking I was already on the not inclusive thing, but 0 to 3 is how we specify GCG. Okay. If we want to get the second one in the loop, we add 1 to both of those, and we get CGC. Okay. Then the last one is text 2 to 5, and this is right. It's not actually going to try to get 5 here because it's not inclusive of that last number. We get GCG. Okay. Now we need, when we put this in a loop, we need it to stop here. Otherwise, it's going to slide off the end. So if we went one more and went 3, 6. It slid off the end and it only got CG. Okay, there will be some instances where I say, that's why I have this here, where it might give you a list index out of range. Right. Once it slides to 5, 8, 5, 9, 5, 9, it's got nothing. That's interesting. I wonder if it's just because it's in Spider, or it doesn't really matter. You get the idea. Once you've slid off the end, you're no longer even potentially matching anything because there's nothing. It's not even 3 base pairs long anymore. Your window isn't. Okay. So how do we make a loop so that we can basically slide across the text and get one window at a time? Well, we need, first of all, what's the general expression for the start position of the last window? So where do we want our loop to stop is basically what we're asking. And it's important to know what's the general expression, because we don't know how long the text and we don't know how long the pattern that Rosalind is going to give us, or more generally, if we're using this in another context, we're not always going to know how long is the DNA sequence or how long is the k-mer that we're trying to match, right? So the pattern is the k-mer. I'll say this again, but right, just so it's clear, the k is 3, and in this case, we have a specific k-mer that is GCG. But in general, a 3-mer, right, just like we talked about 5-mers or 9-mers, this is a 3-mer that is GCG. Okay, so what's the general expression for the start position of the last window? Well, what do I mean by that? It is, no matter how long the text would be, or our DNA sequence, how do we know what's the last window, or where the last window starts? And in this case, it's 2. So long is the text? The text is actually 5 base pairs long, and the pattern is 3. So if we went 5 minus 3, we would be back at 2. So in general, that the start of the last window is going to occur at whatever your length, whatever the length of your text is, minus the length of your pattern. And just as an example, you know, if I made this a 5mer, for example, just for pretend. And then now we set up our loop. Our loop can really only go one time. So it's going to go 0 to 0. Okay, so because the start position is 0, and then you can't move. So, it, you know, maybe that's a silly example because you wouldn't want to put that in a loop. Okay. But if it was 4, it would loop on 0 as a start position, and then 5 minus 4 is 1, and it would get 1 as a start position. Okay. And then we have, right, the example we have of pattern of length 3, it's going to get 0 as a start position, then 1 as a start position, then 2 as a start position. Okay, ideally. So let's see if we can make that happen. Right, so write a for loop that slides across any length of text and pattern. So what does that look like? And you should pause the video here and do what I'm telling you to do. Try to code it first for yourself. So I've already, in my example, and if you're following along in real time, you've already got this much code, right? You've got text and pattern defined, okay? And what you're gonna try to do is write the for loop so that it has the correct range. That's the trick, okay? How do we specify the right range here? And you can go back to P16 and look at how you specify for loop with a range, right? Remember this, you have start colon stop, where the stop position is not inclusive. And then make sure, right, inside that for loop, put a print statement so that it prints the I in your range, and you should be able to get 0, 1, 2. Okay, so pause the video now, try to code that for yourself. Okay, and then when you're sufficiently frustrated or after you've gotten it, you can play the video again and see if you come up with the same solution that I am about to show. Okay, so we don't need to count 0 now yet because we're not actually counting. We're just gonna write the for loop for I in range. And so now is the I guess not really tricky part, but where you test whether you sort of understand how to index those ranges. So, right, what's the general expression for where you want to stop this loop? Okay, so the 0, we're always going to start on 0. It doesn't, if you don't specify a starting position, it will automatically start on 0. So we could do a range that doesn't have anything there, but let's do just to, I'll show you when I finish coding. So we want to go from the length of the text, whoops, why did I put colon, to the length of the pattern. right? That was our general expression on, right, for the last, like, where do we want to stop this loop? Length of text minus length of pattern. But that would give us 2, right? And in fact, because when we do range, range is also not inclusive. So we're going to have to add 1. Now, let's see. If we just did that, right? This is the whole reason I suggest you put a print statement in there and see how it goes. I get my list syntax and my range syntax mixed up often, right? So when you're specifying the range, and I should have known, right? Range has parentheses, not brackets. Usually the commas go with the parentheses. It's just something that you have to remember. So this statement, my output was 0, 1, right? And I already gave away the reason for that, because even though this evaluates 0 and then the length of the text is 5 and the length of the pattern is 3, so this piece evaluates to 2, but because range is not inclusive, it's only printing 0 and 1. Okay, so I need to add 1 there. So now it's going to go to length of the pattern plus 1. So 2 plus 1. Now this thing evaluates to 3, and I get my 0, 1, 2 printed out. Now, what I started to mention earlier is if you leave off the start position, this will evaluate, just go that far. Okay, so you get the same thing. So we're good on, now we've just written a loop that gets us the start position for each window. Okay, so that's going to zip down the string as far as we need to. So we've gotten to that stage right there. Now, the next step, once we're sure that we can get the start position, is to see if we can get it to print the actual window. So instead of over here printing I, we need it to print what's actually in the window. So we needed to get it to print the text 0 to 3. Right, so again, this takes a little bit of thinking about how do I specify text 0 to 3? Like, how do I specify these inside the loop? So you should pause it again here and try to code that yourself. All you're doing is modifying this print statement so that instead of printing I, it's going to print the actual letters of text, right? You want it to print text. Figure out how to specify these in terms of the variables. All right, so pause now and come back once you've tried it. Okay, so the first position that in what we want to print is going to be text. And then this, right, we just got done saying, right, print I gives us 0, 1, 2. And that is exactly the positions that we want to start here. So, right, we can substitute I in place of 0, 1, 2. And then we want it to go to whatever the current position is, right? So, for example, on the first loop through, I is 0. We want it to get from 0 to however long our pattern is. Right? So I plus len pattern. Does that get us what we want? So on the first loop, I is 0, and it goes to the length of the pattern, which is 3. Okay, good. On the second loop through, I would be 1. So it will go from 1 to 4, and then 2 to 5. Okay, so that should do it. Hit play, and indeed. So there's our sliding windows. We got GCG, and then it slid over one, got the second window, and then it got the third window. All right, perfect. So only thing left now is doing the comparison, right? So now we just need to count every time we get a match. So if this is the window, right, that we just learned how to specify, and then if that equals the pattern, and right, in this case, it's the actual text of the pattern. So that's going to be GCG every time. And if it matches, then we count it +1. All right, so try to implement this, pause the video. And I keep saying pause the video because if you just keep watching and type in what I type, you take my word for it, you're not learning it. So try to solve this first, because that, trying to do it on your own first is really where you're learning how to implement the coding skill. Okay. So if you're back, hopefully it worked for you. All we have to do is say if that thing that we just, that window equals pattern, then count plus equal 1. And then print count. So once it's all done looping and counting, we're just going to have it print the count that it ended up with. Yes, I got an error. So I forgot my parentheses again. Okay. And hooray, got a 2, which is what we should get, right? Because GCG matches there and there. And if we go back to Rosalind, the sample output is 2. Now, on a lot of these problems, you'll see Rosalind will give you extra sample data sets. So I could take this. This is a terrible way to test. In fact, that's got a new line character in it. But anyway, you wouldn't really want to do that, but you could. For some reason, I got a new line that split that, and I could tell because whoops, it turned some of these black, which means that is no longer in that string of green. So, but that's okay. You could run that code on the same. Oh, I see what the problem was. keep saying you don't want to do it this way, and then actually showing you how to do it this way, right? That is the text, and then there's a new line, and this is the pattern you're looking for. So that's text, and this is pattern. Yeah, so I'm not sure what there was an odd character there that caused it to split and gave me an end of line error here. But then I got rid of that and it counted it and I got the right output. So it gives me confidence that probably my code is okay. But we're going to show like how to not, right, I've said that it's a bad idea to hard code this into your program, right? You don't want to hard code the data into the program because, right, the whole idea is you're writing code that will be useful on lots of data, allow you to solve this problem in other contexts. So that's the sliding window algorithm, and that is enough to solve Rosalind number 10. But let's go one step further and turn this into a function that we can use anytime we want to. And the pseudocode in the Rosalind problem actually anticipates making this a function. So it gives you this notation pattern count, and then in parentheses text pattern, and then at the bottom return count. That is the notation that you might use for something that you're going to turn into a function. So what we want to do, let's get back to Spider here, is let's start a new file, and we're going to do file save as, and put this in our bin and call it all underscore functions. Okay. And then we're going to do def pattern count. And this pattern count is going to be the name of our function. And we are going to pass text and pattern as variables to this function. And then inside that function, we're going to add some code, and basically the code that we just wrote to count how many matches we got. And then instead of printing at the end, we're going to tell the function to return. So the end of a function is always going to return something rather than having, you could also have print statements in there, which will send things to the screen, but typically you don't need that. You just want the function to do some stuff and then return some output. In this case, we want it to do our pattern matching and then return the count. Okay, so I'm just going to go over here, and sometimes you get into issues with copy paste in Spider. I'm going to try it. And what I mean by issues is your indentation has to be correct, right? We need everything tabbed inside of our function definition. So we have our for loop here, but see how it moved the if statement over? That if statement needs to be inside the for loop. And then we also need the count to be tabbed inside of the if statement. And so it's telling me I have an undefined variable here because I forgot to copy paste count. And then return needs to be inside my function. Spider's super handy about telling you those errors. Okay, so actually I'll get rid of some of these blank lines. And then we need to save that. So now this is not something that we can just run because there's no print statement. It doesn't have any data, but this is now a function that we can call. So let's go back here. Let's see, how do we, actually, I'm just going to get rid of all that. So you could just start a new file, but we've got our function defined here and our module. Now let's use it. Okay. So first thing, when we write a program that needs to use an external function, right? This is going back to P9, from all functions, whoops. Whoops, we don't need to say py. Import pattern count. And so that will go to the all functions file and the all functions module, which is what we just created. So making this file is going to make a module, and then we're importing pattern count function from that module. Now let's do with, so rather than hard code the data, right, we're going to try to do this as a, the right way, where we say go get the data from the downloads folder. So I always get my path wrong. I think users GPA. Downloads. I think let's just do practice.txt. And in order for this to work, I'm going to have to make a practice data set for it to work on as data. So we've had this statement before. It's just what's in my practice data now. I even have that still in my practice, in my downloads folder. So let me go find. So I have a file named practice.txt, and I'm just going to make GCG, CG, and GCG. So that's the practice data from Rosalind 10. And now that's in my downloads folder. So now when I call this, open this file, it's going to open that data. Okay. Now, go back here, right? We need to figure out how to do text and then pattern. And you should pause here and try to remember how to do this. It's back, right? I've given you the pointer to P17. How do you read in data? Okay. This is one of those times where it's kind of useful that some of those commands like readline is going to consume the data, right? So you can pause it, try this on your own, and then come back and see if how you got it to work is the same way I did it. One of the things to use to check, remember again, use print statements. So right after you open it, do print text and print pattern and see if it read in GC, GC, and GCG. Okay, so go ahead and pause before you watch me solve it. Okay. So data.readline, and then rstrip, because we want to make sure that we're not getting weird end of line characters. We already saw when I copy pasted how that was a problem. And so just to avoid that even being an issue, we're going to strip all the white space off the end of every line. Okay. And now let's do print text. I'm going to print them on separate lines. Pattern. And then I'll run it just to see. Module not found. I think maybe because this is not saved. File, save as. Save it in my bin. I'll call this ROS10. Now let's see. There we go. It did not like oh, I forgot this. There's an error on rstrip. Now let's try it. Okay, so first error that I got was that it didn't know all functions. So that was because I did not have my code here saved in the same directory with the all functions module. Okay, so it had to know where to look for all functions. So as long as they're saved in the same directory, that shouldn't be a problem. There are other ways that we can tell it the path to the all functions, but I don't want to get too many things going on in one tutorial. So as long as they're saved in the same directory, it should be able to find the all functions file. Okay, so that was the first problem that I solved. The second one, it got the first, like it read the text fine. I got GC, GCG, right? So this part and this part were fine, but it gave me an error on the rstrip. And that was because I had left off the parentheses right there. Okay, so once I fixed that, everything's good. It told me it reloaded the all functions module, but then it printed both. So I'm all good in terms of I've read the data incorrectly. Now I just need to use my function. So, right, if I come back to the PowerPoint, right, it's just use your function to call the pattern count. So right, and look how Spider even knows my function now because it has loaded my all function module. It's already got this. That's super handy. And so I am now telling Python use pattern count function on text and pattern. And print, since I've got it in a print statement, it's going to evaluate this thing and then print the outcome. And remember, what it's going to do is reads in text and pattern, sends these over to the pattern count function. Pattern count function does its thing and then returns the count. And so this is saying print whatever this returns. So if I hit play, I get a 2. And ta-da, it worked. And I am turning my computer into a genie. Or becoming Aladdin. I don't know how that works. Right, so you can solve Rosalind number 10 now. The only thing to do, I mean, you can try it on the practice data set, right? Good. On my practice data set, right, so I did it. I'm turning this thing into the practice data set. One step closer. And if I rerun this, I get 294, okay, just like I would expect. All is well. So now it's just downloading the real data, running that thing, and inputting the number in the submission. And you should be done with number 10. That's it. The next 3 or 4 problems are all really kind of modifying this thing. So that's what we'll try to get through this for Tuesday. And then I will introduce the new stuff that you need to add for the next 3 or 4 problems over the next day or so, and upload another video for that. Okay.